Hi, today I'll be doing question 66, which states air flows through the tube shown in figure below at a rate of 1200 centimeters cubed per second. Assume that air is an ideal fluid. What is the height h of mercury in the right side of the tube? So essentially the importance of this question is to understand how in systems like this one, how airflow, air speed, the rate of airflow is going to affect the other fluids in the system, so in this case mercury, and to what height is mercury being lifted up or affected. So right off the bat, we are given a volume flow rate of 1200 centimeters cubed per second, which equals Q, and two diameters, one on the left side being 2.0 centimeters and one on the right side being 4.0 millimeters. I converted those in terms of radius and in units of centimeters because next I wanted to find the areas. So the area on the left-hand side of the system was 3.142 centimeters squared, and on the right-hand side was 0.126 centimeters squared. Reason why I wanted to find the area was because looking at the system, I knew that there had to be a change in air pressure because the volume flow rate was remaining constant, but the areas of these two sides were essentially changing, so there had to be some change in pressure there. So I used volume flow rate's base equation, which is Q equal to V times A, V being velocity and A being area. And I isolated V to find the velocity on the left-hand side being 381.92 centimeters per second, and the velocity on the right-hand side being 9,532.8 centimeters per second. I used those two velocities next in an augmented version of Bernoulli's equation, which is change in pressure equals 1/2 times fluid density times velocity 2 squared minus velocity 1 squared. I had a little bit of trouble here for a while because for rho, I was not putting in air's fluid density. I was actually putting in mercury's fluid density. And I had forgotten that earlier they had noted that air is considered an ideal fluid in this system. So you had to use air, and it also makes sense that you'd use air because we had the difference in two velocities here, which were immediately in correlation to the speed of air in this system. So the change in pressure came out to be 55.466 kilograms per centimeters times second squared. I then went on to use another equation that was related to change in pressure, which was change in pressure equals rho times g times h. Rho being fluid density again, g being gravity, and h being height. Now, because we're finding the height of mercury on the right side of the system, I immediately just isolated h and plugged in our change in pressure, which we found to be 55.446 kilograms per centimeters times second squared. And I also plugged in our fluid density, which is now not air, but instead mercury's fluid density, which is 0.0136 kilograms per centimeters cubed. It's upside down because we are dividing it. And I also converted gravity into centimeters because we are solving the height of mercury in terms of centimeters. And I found it to be 4.162 centimeters. The only difficult part of this question that I found to really stump me was, in all honesty, rho right here, and not really knowing that I could use air's density. I just didn't assume it because it was a gas, not a fluid. But looking back, saying that it was an ideal fluid, it makes a lot of sense, along with, again, the idea that there are two velocities here directly correlating to air. And yeah, that's all. Thank you.